Have you ever wondered how AI systems decode complex networks, like social media connections, financial transactions, or even the human brain? These are examples of directed graphs where relationships have clear directions. A follows B, or money flows from X to Y. But here's the challenge. Traditional AI models struggle to capture both the direction of these relationships and the overarching structure of the network. Imagine mapping a city's traffic. You need to know not just where roads connect, but which way cars move, and how those flows shape congestion. That's the same problem AI faces when analyzing directed graphs. Most existing methods, like graph neural networks, GNNs, treat connections as neutral, like a traffic map that forgets one-way streets. They miss the directional semantics and can't see the forest for the trees. Enter SVDformer, a groundbreaking framework that merges two powerful concepts: singular value decomposition, SVD, and transformers. Let's unpack this. First, SVD is like a mathematical X-ray. It takes a graph, represented as a matrix, and breaks it into simpler components: singular values, which quantify importance, and singular vectors, which reveal structural patterns. Think of it as identifying a city's main, highways, and side streets. But SVD alone isn't enough. Enter the transformer. Transformers, famous for their role in language models, use attention mechanisms to focus on relevant details. SVDformer leverages this to listen to directional patterns. Picture a traffic analyst who not only sees busy roads, but predicts congestion based on direction. By treating singular vectors as directional guides and singular values as important scores, the model dynamically adjusts information flow, preserving directionality. Here's the magic. SVDformer doesn't guess. It learns to balance local details like individual transactions and global patterns like systemic risks. It avoids oversmoothing, losing fine details, and overfitting, memorizing data. In tests, it outperformed existing methods on tasks like fraud detection and knowledge graph analysis, proving its versatility. So what does this mean for the future? SVDformer opens new doors for AI to tackle real-world problems where direction matters, from neural connections in the brain to cyber threat detection. It's a reminder that innovation often lies in merging old ideas with new ones. Want to dive deeper into how SVDformer works? Hit subscribe and let's explore the math behind the magic together. Let's break down how SVDformer actually operates. The model starts by encoding the graph structure using SVD, which decomposes the adjacency matrix into key components. These components act as a blueprint, highlighting the most critical pathways. But here's where it gets smart: the multi-head self-attention module. This module functions like a team of experts analyzing the graph. Each head focuses on different aspects, like asking, which nodes are most influential? Or how do connections evolve over time? By combining these perspectives, the model captures long-range relationships that simpler methods miss. Then comes the spectral propagation module. This part ensures information spreads through the graph in a direction-aware way. Imagine sending a message through a network. The model routes it along correct paths, filtering noise and emphasizing relevant connections. This helps AI understand not just who is connected, but how those connections shape the network's behavior. Testing SVDformer on 6 datasets, ranging from academic citations to e-commerce graphs, showed remarkable results. On the Amazon CS dataset, it outperformed competitors by a significant margin, excelling in large, sparse networks where traditional methods falter. Its efficiency, thanks to truncated SVD, makes it feasible for massive graphs. But it's not perfect. In highly homophilic networks, where similar nodes cluster, performance varied. This highlights a trade-off. Global spectral analysis works well for some tasks, but local details matter more in others. What's next? As researchers refine these models, we're one step closer to AI that truly understands the complex, directional world around us. Thanks for watching, stay curious, and let's keep exploring the future of AI together. Have you ever wondered how computers decode complex relationships in data, like social networks, road maps, or even protein structures? These are all examples of graphs, where nodes, people, places, molecules, are connected by edges, friendships, roads, chemical bonds. But when those edges have directions, like a Twitter follow or a one-way street, traditional methods struggle to capture the full picture. That's where SVDformer steps in. Think of it as a supercharged tool that blends two powerful ideas: spectral graph theory, which studies graphs through their mathematical frequencies, and transformer architectures, the same tech behind your favorite AI assistants. Together, they create a system that not only understands graph structures, but respects their directionality. Here's how it works. SVDformer uses singular value decomposition, SVD, to break down graphs into their core components. Imagine peeling back layers of an onion to see the essential patterns beneath. By integrating this with multi-head self-attention, like a team of reviewers focusing on different parts of a document, SVDformer dynamically filters out noise, such as random fluctuations in data, without relying on fixed rules. This adaptability is key, especially when dealing with messy, real-world graphs. But the real magic: a directional propagation mechanism that preserves edge directionality. Traditional graph neural networks, GNNs, often treat connections as neutral, like a web of equal-weighted links. SVDformer, however, ensures that a follow on Twitter or a flow in a network is processed with its inherent direction, avoiding the pitfalls of isotropic, same-in-all-directions models. The results? SVDformer outperforms existing methods on 6 major directed graph benchmarks, achieving state-of-the-art accuracy, especially on heterophilic datasets, where nodes tend to connect to dissimilar ones, like a sports fan linking to a music lover. It also scales efficiently using truncated SVD, a shortcut that keeps computations manageable even for huge graphs. But it's not perfect. In cases of extreme class imbalance, think of a dataset where 99% of nodes belong to one category. SVDformer can miss subtle patterns. Similarly, weakly directional graphs, where direction matters less, might confuse its directional focus. Future work aims to tackle these challenges by combining. And that's just the beginning. Stay tuned for more deep dives into the cutting edge of AI research.